How does a quantum repeater use entanglement swapping? Imagine trying to send a secret message across a very long distance, but the signal keeps getting lost or corrupted. That's where quantum repeaters come into play, especially in the world of quantum communication. They are like relay stations for quantum information, helping to extend the reach of secure communication networks. One of their key tricks is called entanglement swapping, which sounds complicated but is actually quite clever. Let's start with what entanglement is. It's a quantum link where two particles share a connection so strong that measuring one instantly tells you about the other, no matter how far apart they are. But the problem is, this entanglement weakens over long distances because of noise and loss in the communication channels, like optical fibers. Directly entangling particles over hundreds of miles is really hard because the signal gets weaker and more prone to errors. This is where quantum repeaters step in. They break the long distance into smaller segments, each with its own entangled pairs. These pairs are easier to create and keep stable. The magic happens when the repeater uses entanglement swapping to connect these shorter links into one long entangled chain. Here's how it works. Suppose you have two pairs of particles, one between nodes A and B, and another between nodes C and D. Nodes B and C are the middle points, where the swapping happens. The repeater performs a special measurement called a Bell state measurement on the particles at nodes B and C. This measurement effectively connects the two pairs by projecting them into a new entangled state. After this measurement, the particles at nodes A and D become entangled, even though they never directly interacted. It's like passing a secret message through a chain of friends, each passing it on without ever meeting. This process is repeated across multiple nodes, creating a long chain of entanglement. To make this work smoothly, quantum memories are used to store the entangled particles at each node until the neighboring segments are ready for swapping. These memories keep the quantum states intact, preventing them from decohering or losing their quantum properties. Since the process can sometimes fail, the system uses classical signals called heralding signals to confirm successful swaps. These signals tell the network when the entanglement has been successfully extended, so the process can continue efficiently. The result is a much longer entangled link, which is essential for secure quantum communication over vast distances. In essence, a quantum repeater uses entanglement swapping to stitch together shorter entangled segments into a single, long-range entangled connection. This method helps overcome the natural loss and noise in quantum channels, making scalable quantum networks possible. It's a vital step toward realizing global quantum communication systems that are secure and reliable.